Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, and this is actually going to be only one video for the entire little video series for the week that we're going to do. We're going to look at transformations, not quite of the 4D tesseract variety. Those are way complex, nothing to look at there. We're not even looking in 3D, we're just looking in 2D. And I do promise for this to be as basic as possible. If you're looking for more advanced transformation types, you can start with this, and I have probably some older videos that refer to things like the rules of transformation, reflecting, rotating, dilating along lines that look like this and not on the origin and things like that. These are going to be a lot more basic. All of them will be graph based as well. Really just plan for my students to do some practice things just for now, and that's basically it. So I'm just going to go ahead and get started, and as you look at this thing here, I'm going to first show you all 4 transformation types. You see 3 here. These are the congruent transformations. And then there will be one that's not a congruent transformation type. And then I'm going to go over 2 examples for each of them, and in this particular order: translation, reflection, rotation, and the last one's called dilation, and you'll see it on the next slide thing that we go through. All right, so congruent transformations. First of all, to know the word congruent, congruent means equal in size and shape. If you've taken geometry, you know what congruent means on that front. So when I say a congruent transformation is the manipulation or manipulations of an object on a 2D plane that do not affect its size and shape, I mean, we're doing transformations that from what's called pre-image to image, they're both still congruent to each other. They might be in a different point in space, they might be oriented differently, they might even be, as a reflection is, flipped over. But its size has not changed, and its shape has not changed. And I'm going to keep saying that over and over again. I'll be saying congruent more often than here. So there's this word called pre-image, which means your original object, and then the image is the transformed object. So if you ever hear me say pre-image versus image, that's what I'm referring to. The black letter F is the original pre-image, and anything that's colored otherwise is just a newfound image upon that. Just making sure you know that when I refer to these transformations, especially if you see things like these little arrows right here, that's what I'm referring to. Okay, so let's go ahead and get started and see what the heck we're talking about here. A translation. A translation is just another way of saying that an object basically just moves. I'm sliding it somewhere else, like left, right, up, down, any combination of those. It does not change its orientation at all. An upright letter F facing regularly will still be an upright letter F facing regularly after its transformation. This particular transformation from pre-image to image goes down a certain amount and right a certain amount, and I'll kind of show you that thing as well. I can kind of just clone this thing. I can bring it down and right, and it ends up being right there. Or of course, if you just see it as one particular slide, maybe it just goes in that particular direction. But if I were to do a transformation in examples that I'm going to do in a bit, maybe it says move down 5 units and move right 10 units. Okay, and this is where I end up. And what's important about this thing is, as you can kind of see these arrows that I have made for this thing right here from the top right corner and the bottom left corner, when we do the things with graphs, we're really going to look point to point, not just for translations, for all of these. A lot of the times it's really nice to just look point to point, meaning this point moves 5 units down and 10 units right to right here. And then this point also moves 5 units down and 10 units right from here to here. But all of them do it. I didn't want to draw a bunch of them, but this point does the same thing. It goes 5 down, and it goes 10 right, and it ends up in that spot. So what's nice is you can do each little point that's like significant and that makes sense to you, and you can make that image show up in the way that you so desire. That's all I want to say to translations for right now, is it has certain movements, either down, right, up, or left, and then it ends up being somewhere else in space there. Okay, a reflection, and again, if the original pre-image was in the second quadrant right here, if you see, a reflection is some sort of mirror flipped image of sorts. And imagine that you went from this letter F to this letter F. It's like I reflected across this vertical axis here, this vertical line of symmetry, or you'll see me have written down axis of symmetry here. Now, pretend like that this line was also a mirror. This is F looking into its mirror. And what's important about a mirror that you need to know for this is 2 things. Number 1, the object travels across the mirror in a perpendicular fashion, meaning if I want to go from this point here to this point here, it's going to travel across perpendicularly across the mirror. Number 2, the distance from the mirror here is equidistant to its mirror object's distance from the mirror as well. Whatever this distance is, this distance also is. So you're going to traverse across the mirror, or the line or axis of symmetry, perpendicularly and the same distance away of the other of its corresponding point. And we'll talk about corresponding points more when we do examples, but that's from that shape to that one. And if you see this here, I let this animate and do this reflection. You can see how blue reflects to be black and vice versa, how one becomes the other. If this flips across this line right here, flips across the line, look where it ends up, black becomes blue, blue becomes black, and green and purple down here if you truly want to do some other flips. Now, if I'm going to look at some other flips going up and down as well, take a look at this. If I want to make black become green, it's going to flip across this horizontal line of symmetry, which means its path is going to be vertical from point to point. We're going to go vertically across, equidistant away, and it goes up and down like so, and same with purple and blue. So again, the reflection looks like that. And it's really important for you to note the difference between reflection and rotation. I'm going to jump to rotation next. Rotation's the most complicated one for people to actually make happen in a lot of different ways, so I'll try my best here. Number one, rotation doesn't go across a certain line of symmetry, but it rotates around a certain point. So what I made for you guys right here was a center point for this object right here. And I showed you kind of this circle right here to show that every corresponding point is going to be equidistant when I rotate this object. I'm going to literally rotate this object for you right now. I can take this object and rotate it like that, and look how black starts right here, and watch it end up where blue is right now. Look at where blue is right now, and now look at where black ends up. I rotated this thing 90 degrees clockwise, and it ends up where blue is. And I can rotate it again another 90, and another 90, etc. I can just keep going around like that. So a couple things to rotation. Number one, points after reflection remain equidistant from the center as they always were. Like this bottom right point right here for the black F is whatever distance away from the center right now, it remains that distance away from the center even after I rotated a certain amount, whether I rotate it 90 degrees, 180 degrees, or 270 degrees clockwise. That's if I went this way. Now, clockwise is like a clock, but you're going to see counterclockwise as well, and probably more often. When you start to get into pre-calc, you'll understand why counterclockwise is used a lot more. Think of your quadrants 1, 2, 3, 4. Think counterclockwise. So, counterclockwise will happen as well. Now, the angle of rotation can be pretty easily determined based on one point to its corresponding point here. You can see that this angle made is 90 degrees right there, but if I was talking about this corresponding point over here, this is 180 degrees suddenly because it now goes off like this. So angle of rotation is going to be an important facet, as well as where its center of rotation is. All of mine are going to be on graphs. They're going to be on the origin at the point 0, 0. So that'll make it easiest as possible. Now note the difference between rotation and reflection. And notice how this, you'll never see this appear in a rotation of a normal object like this F. Think about how this F always swings. It never becomes a mirror of what it ever was before. This F can never be what this green F is right here. This black F right here can never become the appearance of that green F. So always ask yourself if you understand, and not all of your objects are going to be letters, so always ask yourself what the appearance of your object looks like, and if it can ever, through a rotation, become a reflection. The answer is no, but ask yourself as you rotate it in your head, is that becoming a reflection ever, or is that just an upside down rotation? Now keep in mind, this purple one right here becomes this one right here because this is a composition of two reflections. It flipped vertically and then horizontally. But if I completely, whoops, I don't want to flip it, but if I completely eliminated that purple one right there, just please understand that within that, that's after two reflections. Just really pay closest attention to these two right here, because these are the single reflections you'd be looking at when all said and done. Okay, so those are the three congruent transformations. I never changed size and shape. It just changed its place in space, as well as its orientation and its possible flippage. The next one I want to look at here is what's called a similar transformation. No longer congruent. Similarity means that the object maintains its proportionality, that it doesn't become too overly skewed, like too fat or too tall or something, that if it grows big the same amount in every direction. And that's what's called a dilation. A dilation is where you have something that grows or shrinks, and you're going to see these words later, enlargement and reduction. It's going to grow or shrink a certain amount by what's called a scale factor. And what happens is it doesn't just grow a certain amount compared to its previous object, and I'll tell you right now that this F right here is 3 times larger than this one by size. I mean, whatever length this is on the bottom, X, this is 3 times as large right there. That's 3X, that's what I mean. Same thing right here. If this thing right here is y, this height, this is 3y. It's 3 times as large. So not only is everything going to be a certain amount of times larger, but it also enlarges from a certain center. Just like rotation, this thing has a center of dilation. So what I want you to pay attention to is, let's look at this bottom left point here and its corresponding point here after transformation. Whatever length this is here, I'm going to call this again x. This length is x units away from the center. How big did I say this was? 3 times larger? That means that this point right here is going to be 3 times farther away from the center as its previous one. And that's really what I'd probably pay more attention to when it comes to us doing the graphs. If we just calculate distances, and we're going to do them horizontally and vertically, like we're going to say, oh, how far down and over? Oh, let's go 3 times farther down and over, like that. We're going to do things in terms of what's called similarity. Similar triangles, things like that. This is an enlargement from pre-image to image, and this one's a reduction as it shrinks toward its center right here. And this one is twice as small right here. So let me actually go back to this really quickly. The scale factor, so I'm trying to talk quick so I can, because I know this thing can take a long time. Scale factor here was 3, because it's 3 times as large from pre-image to image. This one is twice as small, which means it's half of its size. This scale factor is going to be 1/2. Basically, everything divides by 2. Whatever this original distance was right here, let's call that x. This new distance right here is just half of that, 1/2 of x, like that. So again, half as tall. If this is y, this is half of y, everything like that. That's what a dilation is. So, and it does change its place in space. It shouldn't be changing its appearance unless it's a negative scale factor, which I won't be using. So it shouldn't be reflecting or rotating or doing anything like that. It should just grow from center or shrink toward a center. And it's going to change its place in space, and it's going to change its size. Okay, so that's called a similar transformation. All right, so there are all those. So I started with translation, and then I'll do reflection, rotation, and then dilation. Let's go ahead and look at them in order, 2 examples each. Okay, so a translation here. Again, it's a shift in an object's location, and I'll mention this part at the very end here. Let's look at an example. We're going to translate quadrilateral ABCD 9 units to the left only. And we can count up, down, left, right, etc. And what I'm going to do is I'm going to draw its corresponding image. Now, I'll do it with you one bit at a time, but if you want to imagine what it looks like right now, this entire thing right here is going to end up being 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces to the left right here. Ultimately, when I make my final drawing, it's going to look like this. Okay. Now, you don't get the luxury of just copying, pasting, and dragging over. You're going to have to do 1 point at a time. And that's okay. It doesn't take too long here. And it depends on how you want to do the other points following. You'll see what I mean in a second. So let's go ahead and start with A. And by the way, I'm going to show you a notation here that you're going to do the transformations to show the points that correspond. If I have a point A in my pre-image, you're going to see this thing right here, A with a little apostrophe. This is called A prime. A prime will be the corresponding point in the image to the pre-image. So meaning if I start with A and shift this single point 9 units to the left, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. This new point right here, I'm going to call A prime. So here's the transformation of just A prime right here. Now I can do all of these other 4 points right here, and then I can just connect the dots and I'll be good. And I'm going to go and do that with you right now. Now B, 1, 2, 3, 4, 5, 6, 7, 8, 9, B prime would be right here. So you can see what I'm doing there, and I could count C 9 units to the left as well. If you really want, you could do something like this as well. You could say like, well, C is also, from B, it's 1, 2, 3, 4, 5, 6, 7 units down and 1 to the left. So here, C prime will be 1, 2, 3, 4, 5, 6, 7 down and 1 to the left like that. So it's kind of your imagination how you want to do that, because you know it's a congruent transformation. Then you know that it's going to have the exact appearance of what, 7 down, 1 left, 7 down, 1 left. That's not going to change. And same with D. 1, 2, 3, 4 to the left and 1 up. So D prime, 1, 2, 3, 4 to the left and 1 up like that. Which is, of course, 9 to the left of this point. But that's the point that I'm trying to make there, is you can do either or. And I connect the dots right here because, remember, these aren't the only 4 points that translate over. These segments right here, all these sides and such, they all represent little mini points in your object. Here's a point, here's a point, here's a point, here's a point. All these move 9 units to the left. Connecting the dots just completes that full thing. So there's the transformation there for example number 1. All right, example number 2, translate triangle TUV 5 units right and 7 units down. So now we're going to take all these things here. I'll start with T. I'm going to go 5 units to the right, 1, 2, 3, 4, 5, and not hit a point right just yet. Let's go 7 units down, 1, 2, 3, 4, 5, 6, 7, like that. That's T prime for me right now. And then U, I could either go 5 right and 7 down, but it would be faster for me again to just go, oh, U is only 1, 2, 3, 4 units to the right of T. So why don't I just go 1, 2, 3, 4 units to the right of T prime, and there's my U prime right there. With V, I'll go ahead and go 5 right and 7 down for you this time. Now, if you're really good with the math, you'll know that V is at -2, 2. So if I add 5, I'll be at 3. And if I subtract 7 from 2, I'll be at -5. So I can just go 1, 2, 3, 4, 5, boom, right there. So pretty fast that way as well. You don't have to actually do counting if you know where you're at on your actual graph. If I connect the dots, I'll be right there. There's one minor bit that I put here on the bottom, said if segments are drawn to connect the vertices, you'll make what's called a 3D prism. If you haven't done geometry stuff before, especially 3D things, I don't think this will make much sense. But what I'm saying is if I connect the corresponding points like this, I kind of make the appearance of a 3D object. It depends on how you guys are able to perceive this kind of stuff. But if you know what I mean when I say that I just made a 3D object out of this, awesome. Think of it like a block of cheese or something. I don't know. A ramp. I have no idea. If you can see the 3D object I'm talking about, great. If you can't, whatever. What I'm saying, though, is that it should be a prism. These lines should go parallel to each other like this. These ones would as well. I'm not going to draw it. Anyway, so there are your 2 transformation types right there. And that's translation. All right, let's go ahead and move on to reflection now. Reflections, you are going to be given some sort of axis of symmetry, and you're going to reflect across it. And remember what I said. We move perpendicularly across the axis of symmetry, and we stay equidistant away from the axis of symmetry on either side of it. From pre-image to image, the axis of symmetry will be directly in between. Think of it like a mirror. All right, so reflect quadrilateral ABCD across the x-axis. Now, just like last time, I'm going to give you a preview of what this looks like. Let's first, well, ignore this for now. Just ignore it for a moment. First of all, the x-axis is this guy right here, okay? So if I'm to reflect this thing, it's going to go up and over right here, which means it's going to flip over. It's going to flip over like that. It's going to flip upside down. So if I take this object and if I flip it for you upside down, how do I do that? Hold on one second. Flip up, down. If I flip it upside down, it will look like this. Obviously, the letters are upside down right now. And it's going to actually end up right here, specifically right here, because as you can see, we're going to get certain distances away from the axis of symmetry for all corresponding points. And if you can kind of tell what I'm doing there, see how that kind of makes sense? That reflection there is equidistant in every direction across that. And you might have to tilt your head 90 degrees sideways to know what that mirror truly looks like. Because sometimes I like to see the mirror just as up and down, the line, to really ask myself if I did it correctly. So let's go and erase that, and let's do it for reals this time. I'm going to redraw the axis of symmetry for you, though. And let's go ahead and do this point by point. Here we go. Start with A. A, we're going to go straight up, right, perpendicularly across the horizontal line. A is 1, 2, 3, 4, 5 units away from the axis of symmetry. So I'm going to reflect across it 1, 2, 3, 4, 5 points right here. This is where A prime sits. B is 2 units away, so B prime will also be 2 units away right here. Okay. And so on and so forth, right? So that's how that thing's going to look. Now, if you truly want to do the thing that I did last time, where it was, instead of counting how far away this is, maybe connect this object, you're going to have to know which direction you're changing things now. From B to C, I go 1, 2, 3, 4, 5, 6. Oh, yeah, it's 7 down, 1 left, right? So from B prime to C prime, do I go 7 down and 1 left again? Well, no, this reflected upside down. I still go left, but now I go up. So take a look at this. C prime, I'll be 1, 2, 3, 4, 5, 6, 7 up and 1 left still. It's still left because I didn't reflect my X points. I only reflected my Y points, right? So C prime, see that reflection? It went up here upside down and so on. And D, and look, if you can imagine, D is closer to the axis of symmetry than C is. So D prime will also be closer. It'll be 1 down. So here I go 4 left and 1 up. Here I'll go 4 left and 1 down like that. You don't have to do it that way. You can continue the stuff that I was doing previously. Totally fine. I'm just giving you both outlets because sometimes that just ends up being faster, all depending on what you're doing. And of course, you must connect the dots there because there's the final image drawing after reflection. Okay, this time I'm going to reflect across the line x equals 2. Now, in order to do this, you have to know what x equals 2 means. It does not mean this line right here. X equals 2 is not a horizontal line. This is the line y equals 2. Okay, this is the line y equals 2. You know the x-axis right here? This is the line y equals 0. A horizontal line across there. So x equals 2 is actually a vertical line, all right? It's a vertical line that goes at 2 for x right here, but it goes up and down like that. So you got to know where it is. And in order to do this now, you really got to ignore your axes at this point. This time, these things don't matter for anything, even coordinate pair things. What I mean by that is this point right here for b, for example, was, I think, 8, -2, and this is 8, +2. Now you're not going to see kind of the same numbers, only one changes negative, one changes positive here. Things are going to change. So you got to count everything with respect to its distance from the axis of symmetry. Let's start with u. It's 1, 2, 3 units away to the right. So I'm going to go another 1, 2, 3 units away right here. This is u prime. T is 1, 2, 3, 4, 5, 6, 7 units away. So we'll go 1, 2, 3, 4, 5, 6, 7 units away right here. That's T prime. And of course, V, here's where you don't want to mess up. Right? If I wanted to say something like, oh, you know, maybe someone might think, oh, V goes right here, 4 down and 1 left. No, this kind of starts to look more like a translation now. Notice this didn't flip over, right? I need this to flip. So it needs to be with respect to where U is and flipped over. It's 4 down, 1 left. Now I got to go 4 down, 1 right, 1 further from the axis of symmetry. Or, of course, 1, 2, 3, 4, 1, 2, 3, 4. So there's my V prime right there. And if I connect the dots, I will have, oh, I don't want to use that. Let's use that blue solid line I had before. Thank you very much. And here's going to be the reflection. And hopefully, again, this is, you know, this is geometry based. And in geometry, a lot of things are perceptually acquired. So if you can give yourself the perception, you really got to ignore the axes, but look right in the middle of that line and ask yourself, do I see a mirror image of what's there? Literally, like my hands, do I see a mirror image of what's there? All right. It shouldn't have the appearance of thumbs on the left, on both of them, or right, or whichever way you're looking at it. Thumb should be on the outside or on the inside, you know, like that. So these are 2 reflection examples right there. That one's across a line that's not an axis, and remember which way those go. You got to picture and draw those. Okay, next one's rotation, arguably the most difficult one. And rotation and dilation, arguably the most difficult. Rotation has the toughest part with perception, especially when you don't have something like a sheet of paper to use. I'll do the best I can with you to give yourself the perception of what this looks like, what this means. Just try and work with me here. Good news is both of these will be with regard to the origin. Okay, the origin is your center of rotation right here, 0, 0. That's a good sign. That means you can rely on these axes and the actual coordinate pairs to help you. Okay, first thing we're going to do is rotate quadrilateral ABCD 90 degrees around the origin. Now, I didn't indicate direction here. I should have. If you're not sure which direction, and I put it all up here so you can read this to your leisure. If no direction is indicated, assume that is CCW. That means counterclockwise. If I don't give you the direction, assume it's counterclockwise. Clockwise is this way. So counterclockwise is this way. So if I'm going to go 90 degrees counterclockwise, my object, which was in the 4th quadrant to start with, is actually going to end up in the 1st quadrant. Because remember, it's only 90 degrees. Okay, 90 degrees is really a tough thing to, it's kind of a tough pill to swallow. I'm going to really quickly go all the way back to this thing right here and look at how 90 degrees occurs with this. Here's my center of rotation right here, and 90 degrees has to do with where one point starts to where one point ends up, and the 90 degrees is based on the center of rotation right there. Okay, so imagine here that in this particular example, if I look at A right here, and if my center of rotation is this guy right here, and this isn't how you have to draw it, this is just me giving you the imagination. Here's an imaginary line going from the center to A. A 90-degree rotation counterclockwise would end up kind of looking something like this right here. Here's 90 degrees, okay? If I want to find A prime, it's going to, sorry, that's not perfect. It's not perfect at all. I'm just giving you an example. If I want to find A prime, it's going to be the same distance away from the center as this is, but after 90-degree rotation. what I'm trying to say is this A right here at 2, -5 kind of hugs the y-axis. It's kind of close to it. But after I rotate it 90 degrees, it's going to kind of be hugging the x-axis. It's going to be right here. This is not a reflection. It's not a reflection. If you want me to preview what this final answer is going to look for you, so I can actually tell you how those points are going to work and how I'm going to do this, let's preview what this is going to look like. Let's actually take this object. Let's rotate it 90 degrees together. I'm going to literally rotate this 90 degrees. What's counterclockwise? This way. Boom. And now if I were to place it at the proper spot, because the spot matters, it's all about the center here. A is at 2, -5. A prime, if it's supposed to hug close to the x-axis right here, it's actually going to be at 5, 2. And this is the hard part for people to digest, because it's actually going to use the same numbers, only it's going to swap them a little or change their sign maybe. See, A was at 2, -5. A prime is at 5, 2. Notice how this 5 came from y to x and changed sign, and the 2 changed from x to y and didn't change sign right here. It went from hugging the y-axis to close to hugging the x-axis. One more version of this preview I'm going to show you guys here. It's going to look like this. I'm literally going to rotate the entire graph, and I know that this is the harder one to do. I understand it is. That's why I'm kind of slowly trying to talk through it here. I'm going to group everything together, and I'm going to do a full rotation with all these together. Imagine that I rotated this 90 degrees counterclockwise all together like that. That's where it's supposed to end up. So if you have a sheet of paper, or if you have your head, and you want to rotate it a certain amount, imagine where it's supposed to end up. It's a lot easier with paper. But imagine where it's supposed to end up, and then draw it in relation to that over and over as you go. So like me, pretend like this was my piece of paper. I'm going to rotate my piece of paper 90 degrees counterclockwise, and I'm imagining where every corresponding point will end up. A started at 2, -5. A prime ends up at the equivalent to 5, 2. 5, 2. And that's where I got to draw it. Okay, and so on and so forth. Everything's going to rotate 90 degrees. So we'll try our best. We'll try our best here. So I'm going to go from A, instead of going 2 to the right, I'm actually going to go 2 up. And then instead of going 5 down, I'm going to go 5 to the right. Because again, 90-degree rotation. So 5, 2 is where A prime is. Okay. Let's look at B. And I'm going to rotate this thing. Unfortunately, the A has to stay right there. But that's okay. B is going to end up at 2, 1, 2, 3, 4, 5, 6, 7, 8. It's going to end up at 2, 8. I look where it started. It started at 8, -2. So okay, 8, -2, 2, 8. You can kind of see where I'm going with that. The numbers stay the same because I'm centered at the origin there. All right, let's look at C. I'm going to rotate that. And again, if you had a sheet of paper, you could do this. Some people don't have the luxury of that. You can use what's called patty paper as well. C, it's 9 over and 7 up. 9 over and 7 up. So that's where I'm going to draw it. 9 over and 7 up right there. C prime. Okay. And finally, D. Well, let's see if we can do this without rotating it and see if we end up in the right spot. So D is 3 over and 8 down. So after I rotate that 90 degrees, it's still gonna kind of hug the x-axis, hug the y-axis here. Later it's gonna hug the x-axis here. So let's check out where this thing goes now. 3 over 8 down. I'm imagining 8 over and 3 up right here. And notice it should stay close to A. It should stay close to A prime, just like D stayed close to A. There. So let's rotate that and see if we put it in the right spot. There it is. So right spot right there. So it's harder to teach from a distant view on this one, especially when I don't know what tools you have, right? I have different tools than you do. So that's one of those things that, arguably this isn't the best medicine necessarily. I'm just showing you one approach. You can go from it in that way. It's really about how can you perceive your rotation and where it ends up from there. This is not a reflection. You've seen what this reflection looks like in the same area. This is not, where's my reflection? This is not, here's the reflection. Here's the reflection. Here's the rotation. This is not a reflection. Okay. Okay. Next one, rotate 180 degrees around the origin. 180 degrees actually might be easier for you than a 90. Now, I didn't indicate direction here, but does it matter? 180 degrees clockwise or counterclockwise puts you in the same spot. So it actually doesn't matter for this one. Now, here's the origin right here, which means 180 degrees, it's going to go just right around like that. So anything right here that was in the second quadrant to start, well, actually I'll end up in the fourth quadrant. Okay, so the cool thing about this is whatever your x, y values were to start with for each point, after you do a rotation, this is an example of a rule, it's actually just going to switch their signs. The x becomes a negative x and the y becomes a negative y. It's kind of easier way to look at it like that when you do 180-degree rotations. So v, for example, is at the point -2, 2. When I rotate at 180 degrees, it's actually going to be at the point, switch the signs, to -2. So v prime is going to actually end up right here. And I'll show you the final rotation in the end when we group it all. But that's where v prime is going to go. Okay. U is at -1, 1, 2, 3, 4, 5, 6, 6. So -1, 6. Now it's going to end up at 1, -6 down here. This is u prime. If you can imagine that this thing flips upside down, not flips, excuse me, rotates upside down, it turns upside down here. U was, somewhere, and T was on the, here's U, here's T. Now when I rotate it, here's going to be U, here's going to be T. It's going to be on the other side. So if T is 1, 2, 3, 4 to the left of U, over here it's going to be 1, 2, 3, 4 to the right of U. Oh, whoops, I'm in the wrong spot. That's V. 1, 2, 3, 4 to the right of U right there. That's T prime. Now I'm going to rotate this thing all together and see if this actually did end up where I imagined it to be. And of course you could have rotated your paper, your object, your head 180 degrees and seen if you could imagine what it would have looked like. But if I rotate it, looks like it ends up about in those spots. Not everything's perfect, but that's where it's supposed to go. All right, in those 3 spots right there. So it seemed to work out. I'm going to connect those dots. I can't guarantee to you that I taught you in the way that you're going to make most sense of it right here. This is the best tools that I have for me to you right now. But those are the examples of rotations with that. And to keep in mind, again, this is the center of rotation at the origin, so everything should be going 180 degrees across, just like that. That's 180. Across the center, that's 180. And if you want to look at these for 90 degrees again, here's B, and here's B prime. That is a 90-degree rotation counterclockwise, just like that. So again, the center of rotation matters. All right, final one we're going to do here is dilation. Let's see how we're doing. Yeah, we're good. Half hour. All right, final one right here is dilation. All right, we're going to dilate. I talked about scale factor a little bit before, and I said if a scale factor is more than 1, it's going to be an enlargement. We're going to take something that's some size, and it's actually going to be that many times larger and that many times farther away from its center of dilation. This was actually easier than rotation. I'll promise you that. If it's a fraction like this one, it's going to be a reduction. So I'm going to do it from each corresponding point, though, just like I did the previous ones. It's going to make total sense here. You got to do pretty simple math here. Take a look at the x and y distances from your center. In these cases, you just need their coordinate pairs because your center is the origin, centered at the origin. We're going to do a scale factor of 2. And what I'm going to do is I'm going to take this triangle and each point, and I'm going to double its distance from the origin in the x direction and the y direction. V is at -2, 1. That is 2 left and 1 up. V prime will be twice as far away from the center. V prime, instead of being at -2, 1, will be at -4, 2. V prime will be 1, 2, 3, 4, and 1, 2. Here is V prime right there. It's twice as far away from the center. You can draw a straight line from one to the other, as you saw in probably the earlier part of the video, in the first 10 minutes. And that's where that one's going to end up right now. So I'm basically going to double my points. I'm not going to, you can do this a bunch of different ways here. U is 1 left and 1, 2, 3, 4, 5 up. So now I'm going to double those distances. Instead of 1 left and 5 up, I'm going to go 2 left and 10 up. It's going to go right here. This is U prime. T, you can, and again, you could do this a bunch of different ways. Because our object is also twice as large, you could also say that this distance will be twice as large here. And because it's straight across, it's pretty easy count. This is 4 away. This distance is 4. So T prime from U prime is going to be 8 away. I just double the distances. It's going to be 8 away, and that's where T prime ends up. So you could either count it as T is at -5, 5 right here, and then double that to -10, 10. Or, like I said, double the distances, and you'll be totally fine. So I connect the dots right here. This is going to be a little weird because the image overlaps with the pre-image right here, but this is a proper dilation centered at the origin. If you want to kind of confirm it, if you had a ruler and such, you could look. I should be able to draw a straight line to the center from one of my points through its corresponding point, you know, if I did things well enough. And it looks like they all kind of scale from that center there, out there like that. So cool. It's kind of like shining a flashlight on something and seeing its shadow on the wall, projected or reduced. All right, next one. Let's dilate quadrilateral ABCD with a scale factor of 1/3 toward the origin, or centered at the origin. This will be a reduction, meaning everything's going to be smaller. A scale factor of 1/3 means we're going to multiply our distances by 1/3. It also means divide by 3. And if I set it up correctly, I made all these numbers divisible by 3. All right, let's start with A. A is at the point 0, -6. I'm going to take both these numbers and divide them by 3 because I'm centered at the origin. 0 divided by 3 is still 0, so my A prime is going to be at 0 on X. -6 divided by 3 is -2. So my A prime is going to be right here at 0, -2. That's A prime. It is closer to the center, not farther, because of the the scale factor. B is at the point, if I counted it right, it's at 9, -3. 9 for X, -3 for Y. What's a third of 9? 9 divided by 3? That's 3. So I'm going to go 3 over. And a third of 3 is 1. I'm going to go 1 down. Here's B prime. Everything's going to be a lot smaller, remember. And remember, it's not just 3 times closer to the center. It's 3 times smaller. The object is 3 times smaller. Every part. C is at, I believe, 6, -9. So now I'm going to be a third of 6 is 2, and a third of -9 is -3. Here's C prime. And D. D is 9 down and 3 to the right. Take a third of those. That's now going to give you 3 down and 1 to the right. Here's D prime. And this should make sense in the stuff I said before. What's the distance between D and C? That's 3. Now the distance is a third of that. That's 1. That seems to make sense. I'm just going to connect these dots right here for you. Just like that. All right, this is the last example I'm doing right here. Just to kind of recap there, 4 different types of transformations. 3 were congruent transformations, translations, reflections, rotations. Rotations a bit iffier, I understand that. And dilations, it's a similar transformation where the object still kind of, maintains some dimensionality of what it previously had. Everything shrunk width and height-wise all the same amount, or grew all the same amount there, but they're not congruent anymore. And those were practice things with graphs. I know that I had specific tools that help me. You can use different tools to help you, whether you're doing it on paper, using your head, different perception things. There are rules that help you with it, but I promise you that you'll get probably more confused with it than it will help you unless you always have access to them and you know exactly what they mean. All right, so that'll do it for this one, guys. This is Mr. Robinson. Thank you for watching. Take care.